So far we talked about systems that are completely isolated and no energy can be transferred in and out of the system. But when a macroscopic system is not isolated, then it is possible to transfer energy in and out of the system, and there are two ways to do this. It's either in the form of mechanical work or heat. So if a system is not isolated, then we're going to have um, a change in the energy of the system. It's either due to work done on the system or heat added to the system. So we have two candidates, either mechanical work or heat. So these two are the mechanisms by which we can change the energy of the system. So if you look at an example here, I have system A and system A prime. System A and A prime can interact, so they're not isolated from each other. However, the total system A plus A prime is isolated. So there is a piston in the middle, and A prime basically has a spring. So if the compressed spring A prime exerts a force on this piston, so if there is a force here, F, this is going to be end up doing mechanical work on A. So we can have the first mechanism, compressed spring in the system A prime exerts a net force on the piston, doing mechanical work on system A. So when is the equilibrium reached? When the force per unit area of the piston on the two sides are the same. So because the molecules in system A also exert a pressure on this piston, so we're going to have at equilibrium the pressure on the system exerted by system A will be equal to the pressure exerted by system A prime. So let's call this force F prime, and there is the force F which is applied by these molecules, and if the total area of the piston is area A, then I have F over A is equal to F prime over A. So we have the same pressure on both sides. Therefore, these two forces, the net forces that we're exerting from the left and from the right, should be the same at equilibrium. The other scenario is to have energy transfer in the form of heat. And so here I have system A and A prime. They have a thermal contact in between, so that you can have energy transfer between these two systems. Now at the atomic scale there will be collisions between atoms of system A and A prime, and they're also colliding with the boundaries, and due to these collisions between atoms and molecules there will be energy transfer between systems, so that is in the form of heat. So here I had the scenario where energy could be transferred in the form of mechanical work, and here it is heat. So heat can flow between the two systems. So we have energy transfer at the atomic scale. Which is due to thermal interaction between these two systems. This is called heat. And what is going on the microscopic scale? It is due to collisions of atoms and molecules amongst each other and with system boundaries. All right, so with these two scenarios, basically we reach the change in energy of the system can be due to the mechanical work done on the system or heat added to the system. Mechanical work is the work done by a force exerted on the system, on at least one of the system boundaries, and heat is due to collisions of atoms and molecules at the system boundaries where we have a thermal contact with another system. So in this scenario here, I have defined a system A plus A prime, a system A star, which is isolated, but A and A prime are not individually isolated, and system A has total energy E, has capital N molecules, and system A prime has total energy E prime and N prime molecules. So basically I'm going to ask myself what would happen if these systems were isolated to start with. Well, first of all, since this system A star is isolated, the total energy of the system A and total energy is E, system A prime total energy is E prime. The total energy of the star system E star, this has to be a constant because the system A star is isolated. And what will be the equilibrium state in this scenario? Well, here I'm going to have at equilibrium the most random distribution of energy. So the average energy per molecule on system A is its total energy divided by the number of molecules. This must be equal to the average energy per molecule on system A prime, which is epsilon prime bar. So this will be my equilibrium condition. Average energy per atom or molecule must be the same. If they're not the same, then there will be energy transfer by collisions. The more energetic atoms or molecules will transfer a part of their energy or lose part of their energy during collisions to the other atoms and molecules. So this is my equilibrium condition for this scenario where I have system A and A prime forming equilibrium, thermal equilibrium, and here is the equilibrium condition for mechanical interaction between these two systems A and A prime. Now let's look at the scenario when the systems were initially isolated. So if system A is initially isolated, then it's going to have an average energy per molecule, initial average energy per molecule is equal to its initial energy divided by the number of molecules. And the initial average energy per molecule in the primed system would be initial energy prime divided by the number of molecules in that system. And I have assumed that epsilon I prime bar is greater than epsilon I bar. So the average energy per molecule in system A is less than the average energy per molecule in system A prime. Now, when I form a thermal contact between these two systems, what will happen? Well, what will happen is, because I have excess energy on the right hand side, there must be heat flowing from the right side to the left side until I have the same average energy per molecule in the star system, so which is the total system that is isolated. So when brought into thermal contact, I'm going to see a net energy flow, heat flow from system A prime to system A until I have reached equilibrium. What is the equilibrium? The final average energy per molecule in the unprimed system should be the final total energy divided by the number of molecules. This must be equal to the final average energy per molecule in the primed system, which is the final total energy in the primed system divided by the number of molecules, capital N prime. So this is going to be the condition at equilibrium. So heat will flow until this condition is satisfied. Now I also have for the star system, for A star, I have the final total energy in system A plus the final total energy in system A prime must be equal to the initial total energy in system A plus the initial total energy in system A prime. Basically, I'm having a redistribution of energy between the molecules in order to satisfy the equilibrium condition. This must be a constant. Why? Because A star, the total system, is isolated. All right. Then I'm going to have E final minus E initial, which is the change in energy of system A, plus E final prime minus E initial prime, the change in energy in the system A prime. This should be adding up to 0. So this is delta E, change in energy of system A, delta E prime, change in energy of system A prime. This must be adding up to 0. And what is delta E? Well, delta E is the heat absorbed by system A, which is E final minus E initial, and delta E prime is the heat absorbed by system A prime, E final prime minus E initial prime. So this Q is heat absorbed by A, and Q prime is heat absorbed by A prime. Well, actually, which one is absorbing heat? Because I have assumed that the molecules on the A primes in the A prime system were more energetic. They would be releasing part of their energy in the form of during collisions with the molecules of system A at the boundary in the thermal contact. We would have a net flow of energy from A prime to A, so heat is going to be absorbed by A, released by A prime. So heat absorbed by A prime would be negative. So we're going to call the system A prime, which is releasing its energy with average energy per molecule initially greater than the average energy per molecule in the unprimed system. This is the hot system. And the manifestation of being hot is that energy in the form of heat will be released. So heat absorbed by A prime will be negative, which means heat is not absorbed, it is released. And we call system A with its average energy per molecule less than that of average energy per molecule in the primed system cold system, and this is going to have its heat absorption to be positive. So heat is absorbed by system A in the form of during the approach to equilibrium. Well, there is one more scenario that would be of interest. What would happen if the average energy per molecule on the primed system and unprimed system were the same to start with? So when they're brought into thermal contact, what would happen? Well, because we have already satisfied the equilibrium condition, there would be no net heat flow between these two systems. So let's note that here. So if we had the initial energy per molecule in the unprimed system and initial average energy per molecule in the primed system the same, when brought into thermal contact, we would see no net heat flow occurs because equilibrium condition already satisfied. That is, the average energy per molecule is the same on the two sides. There is no need to exchange energy during collisions because there is no one that is more energetic than the other particles in the system. Okay, so to summarize, when the system is not isolated, we can change its total energy either by doing mechanical work or heat or both. And here is the first scenario where I have system A and A prime, and there is a piston in between, and A prime has a spring, so the spring can exert a force per unit area. It's F prime divided by A, the pressure, and this can cause the motion of the piston until the force per unit area in the unprimed portion is the same. So system A prime can do work on system A until this condition is satisfied, or vice versa. If the pressure on system A is larger, then the spring can be compressed until the pressures are the same on two sides, and therefore we can have energy exchange between these two systems in the form of mechanical work. If the system A has capital N molecules, system A prime has N prime molecules, total energy on system A is E, and in system A prime is E prime. Then if we form a thermal contact, that is to say we allow collisions between atoms and molecules at the boundary, energy transfer in the form of heat can occur, and here the equilibrium condition will be the average energy per molecule on the two sides should be the same, so that there would be no energy exchange, no net energy flow during the collisions. And the total energy of the system must be a constant, because the total energy, a total system, the start system A plus A prime, I have assumed to be isolated. And if the systems were initially isolated, they had an initial average energy per molecule, initial energy divided by the number of molecules, then we have to look at the numerical value of this average energy per molecule. If it is larger in the primed system, when we form a thermal contact between these two systems, because I have excess energy per molecule in the prime system, during collisions this energy will be transferred in the form of heat to the to system A until I satisfy this condition, average energy per molecule on the two sides are the same. And if you look at the total energy of system A star, uh, just at the point when I form the thermal contact, the total energy of the system is initial energy of the unprimed system plus the initial energy of the primed system. This must be equal to the final energy of the unprimed and primed systems, the total value, because A star is isolated. And this tells me that there is net change in the energy of system A, which is heat absorbed by A, net energy in system A prime, which is heat absorbed by A prime. And if the initial energy, average energy per molecule is larger in system A prime, that we call a hot system, and heat absorbed is then negative, so heat is released. If the average energy per molecule in the unprimed system is less, then we call it cold system, and heat will be absorbed until equilibrium is reached. Average energy per molecule is the same. And finally, if the average energy per molecule in the unprimed and primed systems were already same to start with, when we form a thermal contact between these two, there would be no net heat flow because the equilibrium condition is already